Hello, we are Team A, and this is Human Activity Recognition, our research project using accelerometer data to classify human movement types. With the growing popularity of human activity sensors, the availability of movement tracking data continues to increase, opening a wealth of opportunities for applications across industries. The primary objective of this analysis serves to produce and recommend a model capable of classifying movement types provided a specific set of temporal accelerometer data representing 3-axis acceleration measurements. Following initial exploration of the data, our analysis attempts to predict classifications using the original data in its raw form. We then enter an iterative process of feature engineering and change point evaluation, further improving our model performance before coming to our final recommendation. The data used for this analysis is derived from the results of 4 users wearing independent sensors on their waist, left thigh, right arm, and right ankle. Although the dataset is comprised of over 100,000 observations, these are illustrative of the characteristics of only 4 users. This brings into question some aspects of the external validity of a model when generalized to an entire population. To protect against such threats to generalization, the analysis implements a method of user-fold cross-validation, in which the data is trained and tested in 4 iterations, with each iteration holding out a single unique user's data to be tested and validated. This allows us to assess how the results of the model will generalize to a sample-independent data set and gives us a better idea of its performance in real-world application. Complemented by this method of validation, our analysis evaluates 4 different machine learning models, specifically logistic regression, random forest, naive Bayes, and K's nearest neighbor, across the metrics of accuracy and area under the curve. Area under the curve, or AUC, provides a unified means of overall expected performance of a classifier by calculating the total area under a receiver operating characteristic curve, or ROC curve. An ROC curve visualizes classifier performance by plotting true positive rates against false positive rates of a classifier, with the optimal point being where true positive rate equals 1 and false positive rate equals 0.
When making instantaneous predictions on the raw data, our random forest performs highest, with an AUC score of 0.7838.
Additionally, observing the ROC curves, it is interesting to note that all the tested models appear to have the most difficulty classifying the transition movements sitting down and standing up. Furthermore, all 4 of the models far outperform the default model, which is represented by the dashed gray line at the 45-degree angle. Considering in real life that movements are typically sequential, for instance you cannot sit down if you're already sitting, our analysis next explores the temporal nature of the data in an effort to improve model performance and evaluate change point detection. By deriving a windowed mean feature, we are able to smooth the data in such a way that presents clear boundaries between classes. However, as the variance of the observations range drastically across classes, deriving a rolling variance feature across windowed data allows us to capture this relationship despite the earlier smoothing. We find the temporally derived features to be highly informative as we improve random forest model performance, increasing AUC from 0.7838 to 0.9465. Our analysis finds a window size of 10 observations, or 1.5 seconds, provides the greatest benefit in terms of real-world applicability, as the marginal increase of the AUC score diminishes significantly at any window size beyond this point. Observing a time series of actual versus predicted classes, we see that although there are certainly cases of misclassification, most notably of the transition movement types standing up and sitting down, temporally the change point detection appears quite accurate. Finally, our analysis investigates the classification performance if only a single accelerometer is to be worn. Sensor 4, which is worn on the waist, and Sensor 2, which is worn on the left thigh, provide the highest AUC in terms of single sensor model. However, as may be noted by the ROC curves, Sensor 2 also classifies best those classes of highest relevance to real-world application: sitting, standing, and walking. With this in mind, our analysis recommends a random forest model tuned to take advantage of the temporal nature of the data, deriving features of rolling mean and variance as inputs conditional on a window size of 10 observations, or 1.5 seconds. Furthermore, our model recommends the independent use of Sensor 2, which is worn on the left thigh, when implemented in most real-world applications. It should be noted that our analysis realized the greatest performance when utilizing all 4 sensors simultaneously. However, we do not feel this is practical in most real-world applications and would likely increase costs significantly. If implementation time is not a particular concern, our primary recommendation is to revise the sampling method to present experimental conditions that better reflect real life. For instance, monitoring users wearing sensors performing regular activities rather than instructing performance of movement types. We also recommend an increase in the number of users observed during sampling in order to capture input characteristics more representative of the population as a whole. Finally, if implementation of the model in real-life application is time-sensitive, our analysis recommends the immediate launch of a beta program using the recommended random forest model deriving windowed mean and variance features. This not only allows for decreased cost acquisition of data that better represents the real temporal nature of movement types, but a collection of years that increasingly better represents the population through introduction of the product to a real market segment.